Now what we care about, because it's connected to bonding and all that sort of thing, is where is the electron? So we like to find where the electron is. And I'm not gonna do any proofs for you, but if you take quantum mechanics later, you'll see that's related to actually psi squared, or the wave function squared. Can actually tell you where the electron is. So let me redraw this graph. You wouldn't have to draw this, but hopefully it makes some logical sense here. The nodes are still at the same places, so I'm going to redraw the nodes. Now what happens when I square this, it'll just get bigger. Hopefully that makes sense, right? What happens when I square this? Because it's negative, it will be positive, right? A negative will become positive, it will become bigger. And because they're equal weights, they'll all be of equal size. Okay, so it'll be symmetric looking. And this will be psi squared versus x now. Psi squared is something called the probability density. The probability density of an electron. Okay? And what the probability density represents is the probability of finding an electron. The bigger psi squared is, the more likely you will find an electron there. So where am I likely to find an electron? Here, up top here, or down here? Up top, because psi squared is numerically larger, and so you're more likely to find an electron there. Okay, so there's 3 places where there's a high probability of finding an electron. Why will we not know exactly where the electron is? According to what principle? Heisenberg uncertainty principle. It's all related to probability, but we don't know for certain where it is. But there's a high probability to be here. There's pretty much 0 probability it'll be at a node. Okay? So at psi equals 0, the electron will not be there. The electron will not be at psi equals 0. But it's a high probability. It's at the top. Partial probabilities it'll be at other locations. Okay? So you need to know about the probability density, which is psi squared. Probability of finding electrons somewhere. Okay? Alright, now we're ready to go to 3 dimensions. That was just an appetizer. When you go to fancy restaurants, which I'm sure you do all the time, and you go to McDonald's and you get your fries out. Now we're ready for the meal, the Big Mac right now. Okay? And this is the 3D wave function. Okay? And we're kind of getting into we're on the page around 65 right now in the reader. Okay, in 2 dimensions, you have the x and the y-axis. Is that okay? In 3D, you have the x, the y, and the z-axis. Okay? But that's Cartesian, and that's so boxy, meaning it has right angles. However, these electrons move in a curvaceous manner. Okay? They have a lot of curvature. So it's, what kind of coordinate system do we use when we're talking about curvature? Somebody know from math, maybe 7th grade? There's the polar coordinate system, but that's r and theta. That's only 2 dimensions. A spherical polar coordinate system, r, theta, and phi. So you're going to see these. R is a distance, and there's 2 angles, theta and phi. You might be thinking, oh, I don't know what those angles mean. That's okay, I have a picture. This is the spherical polar coordinate system. Okay, brace yourself during this part of the lecture, okay? You might need to keep on holding to your neighbor, even though it's not dark. Everything in your mind is going like blink right now. So r is the distance from the origin. Theta is the distance from the z-axis, and phi is the distance within the xy plane, or the angle within the xy plane. This is a spherical coordinate system, and this is how they're related to x, y, and z. Again, you won't have to do calculations of these, but you're going to see r, theta, and phi as we go through this next section. So I wanted you to know where they come from. These kind of definitions are also given in the reader, and that figure precisely right there is in the textbook somewhere. That's on page 273. Okay, so now you're like, where the heck is this going to go? Now, So before we had psi of x. Now that's going to, for 2 dimensions, for 3 dimensions, we'll have psi of x, y, and z. But we prefer curvaceous nature, so we're going to say psi of r, theta, and theta. Okay. Really, you could use either Cartesian or the spherical polar coordinate system. Though we'll find the textbook uses the spherical polar. In the reader, I'll use both just so you can see both. Okay. Now now we got to do more math craziness here. Okay. Let's say I had a function. I'll use f, because we like the letter f. Function of x and y. And let's say that function is this. X squared y plus 3xy. Okay? Just as an example. Okay, is it okay that I can factor out y out of this? X squared plus 3x. Okay, I factored out y. So now I can make a new definition, and I can say, oh, I have a new function, capital X, which is equal to x squared plus 3x. And then I have another new function, capital Y, which is equal to y. Is that okay? So that f of x and y is equal to capital X as a function of x times capital Y as a function of little y. Does that make any math sense? Do I need to say that again? Basically, I'm saying that y can be factored out, and I have 2 new functions which can be multiplied together. One is fully composed of x, variable x. The other is fully composed of variable y. Okay, if you get that, then we can move on. So now, let's go back to psi. Going back to this function now. This function, it turns out when you do the derivation, we're not going to do that. You'll do it probably if you take quantum mechanics in chemistry or physics, you can do this kind of derivation. You can derive the functions for psi. For example, in 2D, it was sine n pi x over L. That was the function, was a sine function. It'll be something like that here, just a little more complex because we're talking about 3 different dimensions. Okay, so we can actually end up factoring the r part, the distance part, from the angles. Those can be factored out, and this is how they do it. They define a new function, capital R, to be a function of the variable r, and then they define another function, capital Y, to be a function of the 2 angles, theta and phi. Okay, so the r part of the 3D wave function can be factored out of the angular part of the 3D wave function. And we don't just stay there, we give everybody a name, because everybody has their own special identity. This is the radial wave function, and this is the angular wave function, making up the total psi wave function. Okay, so the radial and the angular part of the wave function. Okay, just names. That's it. Okay, now let me show you what those wave functions look like. Remove this. Okay, this probably of this chapter is the scariest moment. Okay, these are the wave functions. Page 66 of the reader, and in the textbook, let me see where that is. I don't quite remember. It's page 276 in the textbook. Okay, all right, I'll let you process it out for a second. Freaking out. You want to memorize them? You can if you want. I have some of them memorized myself. Okay. But you don't have to. All right, now let me explain them. The left-hand side, see the y, the angular part of the wave function, the first 2 columns. The right-hand side column, the last column, is the radial part of the wave function, capital R. So you see the R part has all, well, let me get this part. The y's, for the first column, all have thetas and phis. sine and cosine functions. The middle column, it's not in your book, but a lot of people have asked me, so I put them in here. This is the Cartesian way of writing it. Okay, so as far as x, y, and z. So the middle column, we can do x, y, and z, that's possible. That's what the middle column represents. The last column, we make a substitution. You see in this bottom box right here. Sigma, the lowercase letter sigma, is a function of r. And then, so you'll see all the radial wave functions are functions of sigma, which is a function of r. And they all have e to the power, so they're all exponential. They all have exponential decay. All right. You might see these from time to time, but we're really not going to use them. Okay? But I'll tell you the purpose of them as we progress. Okay? Does that make sense? Hopefully that calms you down a little bit. You'll see on older practice exams where we have in older videos that I've posted on YouTube, there have been times I've actually used these, but that has kind of over time been written out of our curriculum. So we're not going to be using them directly anymore. But older exams will. All right, so what the heck do we do with that? We're going to take an interlude right now. Because that is too freaky to look at, we're going to do section 7. We're going to postpone thinking of those functions for a while until I cover section 7, and then we'll come back to it. And it'll all connect in a beautiful, wonderful way, or you'll be really confused, one of the two. Okay, we're going to talk about something called quantum numbers. Or, I guess as far as your quantum hashes. Okay? Quantum numbers as far as I'm concerned. And I'm going to describe a couple things that we call quantum numbers. Okay, so we're taking a little pause from the wave functions for just a little while. Okay, quantum numbers. There are 4 of them. I'm going to teach you 3 right now. The first one is n. Hey, remember n? That old n from before? This is the same n, and now you're going to learn a little bit more about it. N is called the principal quantum number. Principal quantum number. It is, as you already know, a counting number. 1, 2, 3, etc. It's a counting number. What does it represent? The larger n is, I already told you already, does energy go up or down as n goes up? Yeah, as n goes up, energy goes up. So n represents energy, and remember it also represents orbits, right? So as you can imagine, the more orbits you have, the bigger it gets. So as n increases, 2 things will increase, the size and the energy. So n represents size and energy. By the way, if you're wondering where we're in the textbook, we're going to, on the reader, we're page 67. The textbook, we're on 273. All right, so n represents size and energy. It's called the principal quantum number, and it's a counting number. Here's the second one, L. You might have seen these in high school before. It's not the same L. This is a lowercase l to distinguish it from the L we saw a little earlier, the length of the box. This is not that L. This is a different L. This is called the angular momentum quantum number. Angular momentum quantum number. L is a counting number, but it starts at 0. 0, 1, 2, dot, 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 etc. So it's always at least 1 less than n. Okay? L and n can never be equal. L always must be smaller. Okay? L is always smaller than n. So write that. L is always less than n. Okay? This represents shape. This represents shape. Okay? How does it do so? Let me write this. I'll write out 3 also. 0, 1, 2, 3, etc. And you'll see the connection in a little bit, really, not quite yet, but if you know these letters, you'll know what I mean. Because n is a number and L is a number, and we don't want to confuse the two, we put almost arbitrary letters for L. So when L is 0, we call that the letter S. When L is 1, we call that the letter P. When L is 2, we call it the letter D. When L is 3, we call it the letter F. And you'll see how that connects to the periodic table later. But you need to know, if I say L is D, I mean L is the number 2. Or if I say L is 3, I mean L is the letter F. They're interchangeable. And these letters stand for words, which you can see in the reader if you're interested. Okay, that's the third quantum number. It represents shape. Each of one of these will have a different shape that I'll tell you in a little bit. Let's finish the third quantum number first, and then I'll talk more about the shape. M sub L. This is the magnetic quantum number. Magnetic quantum number. M sub L is a little different, but it's also a number. It's bound by negative L and L, and it includes both of them. So it's between L and minus L. So M sub L is totally tied to L. Okay? So for example, if L is 0, and I'll illustrate this more later, but if L is 0, M sub L would be 0, because it's between 0 and 0. If L is 1, then M sub L is between 1 and negative 1. So it would be 3 possible numbers, 1, 0, minus 1. Okay? And you'll see me write this out in a little while later. What does this represent physically? This represents orientation in space. Which way is it oriented in space? Up, down, right, left, etc. So it represents orientation in space. Okay. Now let's come back to L for a moment. L could be 0, 1, 2, 3, etc. That goes with the letters S, P, D, and F, etc. S has a certain shape, as I told you earlier, and that's a sphere. And in this class, because I assume you are terrible artistically, you should draw a circle. Okay, to represent a sphere. Draw a circle. I don't want to see any fancy three-dimensional craziness. Draw a circle. Okay, P is a 2-leafed clover. Okay, so it's some sort of entity with 2 leaves on it. Okay, those leaves are symmetrical. It comes to a point in the center. Okay. D is a 4-leaf clover. Okay. And I expect you to be able to draw these, by the way, and I'll be more specific on how to draw them a little later. I'm just kind of introducing the topic for you. So this is D, S, P, and D. F you won't have to draw, but if you're curious, and I'll bring some pictures later, the next lecture, it's an 8-leaf clover for the most part. So, but I can't imagine looking at a picture of you drawing an 8-leaf clover, so we're not going to do that. Too tough for normal humanoids to draw those. Okay? So they all represent different shapes, and we'll talk more about those shapes as we kind of progress onwards. Okay. All right, that cool? I'm going to have to get a whole new slide out now. Let's get a whole slide. This will take, you know how big I write, this is going to take a whole page for me. Okay. I'm going to have a table. First column's N, second column's L, the third column is orbital designation, which means the orbital name, which is NL. Then we're going to do ML as the next column, and then we're going to do the number of orbitals as the last column. Okay, 5 columns. First, N. What's the smallest N can be? 1. Okay, so that's the first value of N. That's the smallest it can be. If N is 1, what must L be? Remember, L always must be smaller, and L starts counting at 0. Okay, the orbital designation is the name of this orbital, which would be 1, 0, or NL. But because that looks like the number 10, we're going to use the letter for L. So instead of 1, 0, we're going to write 1s. And the name of this orbital is called the 1s orbital, or 1s atomic orbital. M sub L. If L is 0, what's M sub L? Has to be 0. If L is 0, M sub L is bounded by plus L, or 0, and negative L, 0. So it's just 0. Okay, the number of orbitals is the literal number of values you see here. There's one value, a 0, so there's one orbital. The number of values in the M sub L column tells you the number of orbitals. Next. Okay. N is 2 is the next one. If N is 2, what's L? 1 or 0, yeah. So it could be either, because both values are less than 2. So it could be 0 or 1. So this would be 2, 0 or 2s, and this would be 2, 1 or 2p. Remember, p goes with the number 1. Okay, if L is 0, M sub L is 0. If L is 1, what's M sub L? If L is 1, then M sub L is bound by plus 1 on one side and negative 1 on the other. So it's negative 1, 0, 1. Or I'll write it like this. 0 plus or minus 1. Okay, so there's one value here. This number is 1. What number would go here? 3. I'm 3 numbers here, a 0, a 1, and a negative 1. That's 3 values with 3 orbitals. Ready to go to the next one? 3. Okay, so this could be what values here for L? 0, a 1, and a 2. It can't be 3 because L always has to be less than N. Okay, so this is a 3s, 3, 0, 3s. It's a 3, 1, or 3p, and what's this one? Yeah, the number 2 goes with the letter D. Okay, so we've got, if L is 0, M sub L is still 0. If L is 1, M sub L is still 0 plus or minus 1. How about this one? L is 2. If L is 2, we're bound by negative 2 and plus 2, or negative L and plus L. So it's negative 2, negative 1, 0, 1, 2. Okay, so let me write all those numbers there. So then, the number of orbitals is 1, 3, and 5. See the pattern? Hopefully. There's 5 digits here, 0, 1, negative 1, 2, negative 2. So there's 5 orbitals. Okay. Last one. 4. We can go on, but we'll stop at 4. It can be 0, 1, 2, or 3. So, if N is 4, L is any number less than 4, going down to 0. So 0, 1, 2, and 3 are less than 4. Okay, so we've got for S, you tell me, for P, for D, and for F. There we go. So these letters correspond with L, as I told you earlier. So then, here we go again. M sub L corresponds to L, and that's 0, 0 plus or minus 1, 0 plus or minus 1 plus or minus 2, and then now 0 plus or minus 1, plus or minus 2, and plus or minus 2. So if L is 3, M sub L is bound by plus L and minus L. Okay? Or plus 3 and minus 3. So it's minus 3, minus 2, minus 1, 0, 1, 2, 3. Okay, and about the number of orbitals are 1, 3, 5, and 7. Just following odd numbers. Okay? So that's how the quantum numbers work. Let me give you a couple terms. These here, N, these are called shells. Those are called shells. So N represents the shell number. These here are called subshells. They're shells within a shell. so subshells. And the last two columns represent the number of orbitals in a subshell. Okay, the number of orbitals within a subshell. So here's the whole picture. I don't know if it would fit. Barely. Okay? So what does this mean? I'm going to move this for a moment. I'll put it back. Remember the Bohr model of atom where n equals 1, n equals 2, and n equals 3? There's actually fine structure now. When n equals 2, there's 2 of them. When n equals 3, there's actually 3 of them. So there's fine structure to each orbit that we didn't know about before. Okay? Where there's multiple orbits within an orbit, or subshells within a shell, as we say. All right, I know your brains are like, ooh, this is amazing.